Hey everyone, welcome to hardwear.io webinar. Thank you so much for joining us today. I know it's a Friday evening, but I assure you all the next 45 minutes would be worth your time, as we have two very special guests, Cristofaro Mune and Nick, who have more than a decade years of experience in hardware security. I would like to also congratulate them for starting their new company, Realize. Today, they will talk up to us about how fault injection attacks are and how they can simply bypass the secure boot check for devices. Additionally, if you have any questions, please send them across via the Zoom chat. We would take them after the webinar presentation is complete. They will be also delivering two trainings for the upcoming hardwear.io on TE Core and Secure Boot. So those interested, please do join us for the trainings on the 27th to 30th of September. And like everybody else who goes to conferences, we all love enjoying to socialize and make new friends and meet new people. So those who are interested in our hardware.io social networking session, please sign up for the hardware.io fix up session, where we would match you with another attendee of our conference based on your technical interest and security experience. So without any further delay, Chris and Nick, I would like to welcome you and join and go ahead with your presentation.
Thank you very much, Antrich. Cristofaro here, and nice to talk to you. Thanks for inviting us. And let's start with our presentation. And yeah, you should be seeing the slides now, right?
Yep, you can see the slides.
That's great. That's great. So thank you, everybody. It's Cristofaro, and also Niek is here. We are from Realize. We like playing with a lot of things, especially fault injection stuff. And today we are going to discuss how we can use fault injection for bypassing an encrypted secure boot in general without having the key. This has been historically an important problem or important assumption in the case, even from Smartcard, that if you have an encrypted secure boot, then you cannot apply the usual attack, but you still need the encryption key in order to create your malicious firmware. Well, research has advanced, and we actually like and enjoy to be part of that, and we show how this is possible. But let's get started without further ado. Let's give an overview. All boils down to our research that we did in 2019, where basically we turned data transfer into code execution. So basically, you're transferring data between devices and between different subsystems, and you turn that into a code execution. So we also performed multiple DMFI attacks on the SP32 chip in order to explore the implication of such research, because that was actually was the goal. So we first start with the characterization of the target, then we just bypassed the simple secure boot, then we bypassed a secure boot using our technique. So controlling PC. Then we used also this technique for bypassing flash encryption and to extract plain text data. So basically, this is what we are going to show and discuss today, and we hope that you can find that interesting. So it's important to share that all the details in this presentation were disclosed to Espressif as earlier this year. Also, the CV have been assigned, so everything that we are discussing is actually now public, and fixes may be available depending on the impact of your device, on your device. Well, our company has just started, as Antrich mentioned. We like to advise, give support to analyze and test device security in general. So we like device security in general, and even the components, of course. And we do provide our services to manufacturers, to 3D labs, or even to in our lab for our pleasure and research. we do training. We will have the great honor to be part of the hardwear.io training session with both with T-Pound and Bootpound, where we actually are going to break only by logical means, and so we're not going to use hardware attacks, breaking TEs and secure boot. And finally, as I was mentioning, this is what we like to explore: device security, low-level software, and in general fault injection, or whatever is between hardware and software at the boundary. But let's go right into the topic for today. So we want to bypass secure boot using EMFI. That was the first step that we wanted to do. Remember, I mean, we first wanted to see if our equipment worked as we wanted to work on a target we were already familiar with. And also because the target was not explored already in terms of being vulnerable to EMFI, we want also to have a look at that. So our approach for this initial step was we just reproduced what was already published by Rescue and limited results. We decided to use EM instead of voltage because even if we are just trying to see if our equipment works, we want to bring something new. Also because the target, we didn't know if it was vulnerable to EMFI. But EMFI has a few advantages, we think, with respect to voltage nowadays in general. Well, generally, there is no invasive target modification which is required. You need to solder stuff. You need just to be able to pinpoint what to do and where. And also, the injection technique is quite different. So you are introducing different faults and triggering different vulnerability. It's quite easy to understand what is vulnerable, what can be triggered by a voltage glitch is not necessarily what can be affected by the NEM pulse. So we regard this as two different techniques, and probably the components which are sensitive to these two different techniques are actually different themselves. Let's have a look to our target. I assume that some part of the audience will be already quite familiar with it. We have a 32-bit Extensa LX6 CPU. It has internal and external memory. And we're going to see some of them in the next slides. And there are many peripherals in the interface, and it's a very interesting SOC for building IoT devices. I mean, both for low cost, but also for the powerful capabilities it has. It also has a few hardware-backed security features like secure boot and flash encryption, which makes also an interesting target for hardware-oriented research, or especially for fault injection in our case. So for us, fault injection, it's a matter of it's basically introducing faults into a chip in order to alter its intended behavior, and that's what we think is a quite general definition of fault injection, and we have been sticking to that for quite a few years now. So in general, you would have, let's say, the typical example that is presented is where there is a check, security feature. You are checking something like secure boot. If secure boot is enabled, then you perform the authentication and then you execute. So basically, you can use fault injection in different ways in order to target this conditional, this decision made by software. And we have many examples in years that this has been possible. Okay, this is great. This is interesting. It all boils down to the assumption that hardware should work as intended, but you make it work outside of its usual behavior. The way we start usually is, let's say, exploring the target. This is the setup that we actually used. Keep in mind that for doing this research, you don't necessarily need this setup. You can do these what we did basically with any equipment. So don't be scared. It's what we had available. It's what we are used to use, and so you are free to repeat the research, of course, with completely different equipment. So having said that, where you see what you see on the screen is the SP32 as our target. So we have a UART for communicating with the target, with the TOE here. We have an EMFI probe. electromagnetic fault injection probe. And we also have an XYZ stage, which allows us to move the probe on top of the chip. And then also we have an FPGA-based tooling, Spider code here, which allows to answer to different inputs, produce different output, and in a timed way. So basically we use this for triggering our own attack. So there is nothing more than this in our equipment. Well, the first step that you want to have is always understand if the target is somewhat sensitive to your technique, because in the end you might be using a completely wrong technique that the device overall is not sensitive to, or you might be using a technique which is too difficult to control in order to get some result. So the first thing that you always want to do is seeing if your technique has some kind of effects. The way we usually do it is by executing some code on device. Keep in mind that you don't need necessarily to be able to run the code on that specific sample. You might have another one, but you need to have an idea. It's better if you have an idea that if your target is sensitive to the technique you're using. So what you're seeing here is just a loop, and it's an unrounded loop written in assembly. What do we do here? We just put the trigger high as a signal, so we are able to measure the signal. We know where the loop starts. We start setting the registers here in order to have some pre-computed values in our register with known values that we are able to check after the loop is completed. We then increase the counter for 10,000 times, and then once we are done, basically we output the counter and put the trigger low. So basically, this helps us to understand from the output, which should be something that we know. So the counter should be 10,000, and the register should be should have that value or that specific value which we set initially. By checking all these things, we are able to understand if there is some kind of effect on the target on what with what the technique we are using. So, for example, the expected result here is 2710. Then here there are a few markers which are helpful for us, and you can see there is one success here, which is 2708. Let me make it a bit bigger. Do you still see the slides just to check it? Yeah, great. Okay. So basically, you have a different response, and we know that we've been able to affect the count here. So we've been able to affect how many this loop has been executed, how many times. So this is greatly interesting, especially when you start mapping the behavior to a number of variables that are part of your choice space or your injection space, glitch parameter space. That's how we call it. And for sure, one is the physical location of the probe. So basically, we start doing executing this code. We start injecting during this code while scanning the surface. So we notice it that more or less we had results in our scan in a physical position that was along this side. So basically, we know that if we put the probe here, something actually happens, which is good because it actually limits your search space significantly. So also, this is exactly where we had the single fault that the single success. So we're able to affect the counter. So that is a very good candidate for exploring further the location. So basically, we said, okay, this seems good enough. We are able to affect the loop. Let's say in an old way, you would say we are able to skip instruction. And so this seems suitable as a technique for bypassing a secure boot. So let's just put the probe there for the injection. And now let's try to see what happens. So we also need a way of triggering our attack because, I mean, secure boot, you know, there is a signal verification which happens specifically in time, and you would like to know when you want to glitch. So basically, we started to record the activity on the SPI bus on P1. I don't remember if it was the input on the output, but we started using one of the pin. Basically, we start using this part as a trigger. Why? We assume that signature verification should be done more or less at the end, because we know that it's the end of the loading of the bootloader in memory. So you see the trigger signals we just put here, and this is for us as a reference for saying, hey, start counting from here, and then you glitch after X. So we more precisely focus on this part, which is somewhere directly after the bootloader is copied, so right at the end of this area. So basically now the probe is fixed. More or less we know in time where to glitch, and well, we start experimenting. And what you see here is we measure the power that we use against the delay in time, because of course we don't know exactly so we need a window of time where to glitch. And we find that with this combination, we are able to find this key three kind of success in 35,000 experiments. What is important though, is that after we fix this parameter as well, so this power and this delay, and also we have fixed the probe, so we have fixed already a few parameters, we are able to achieve a successful rate of 2 glitches per minute. Meaning that this success means, yes, we have bypassed secure boot, meaning that we have been able to see and to that the booting is completed successfully with a modified firmware. So at this point, basically, we know that if we are here, we get a nicely secure boot bypass every 30 seconds. And this is quite an interesting one. We usually don't use so much the success rate because that does not give you an idea how long does it take. We prefer this kind of measure of the information in order to qualify how good is our glitch. So basically, what we're seeing is that we are using our tooling, Risk Inspector Refine in this moment. We are using electromagnetic field. Here we are setting our timing in location and power, so location exactly that one. But what kind of fault are we generating? We actually don't know. I mean, in the end, if you just look at the results, you don't even care in the end. So basically, knowing what kind of fault you are generating in this attack is not relevant. You are just able to bypass the signature verification and to achieve code execution. By the way, this is a reference model that we like to use, is a fault injection reference model, which can be used in several situations for describing attacks. For example, we are going to see how changing this part can enable much more powerful attack than just this. If you want to have more information, we have described this in a blog post. Feel free to visit, of course. But this model can be used both for offensive, as we discussed, but also for defensive purposes. I'll let you to read all that on the blog. So now we basically tested our equipment. We just bypassed the secure boot. We did mostly nothing new. We rehashed, let's say, we demonstrated it is possible to do the same thing that has been already demonstrated with voltage, but with EM. But now we are back to our goal. So we are confident that our equipment works, and we can set, let's say, the stage for putting our research into practice. So now we want to turn our data transfers into code execution. So let's assume that we, instead of having content in the bootloader, we just write pointers. We just write that. So there is no malicious bootloader. We just place pointer there. So in principle, if you inject a glitch while the address pointers are copied, because this is being copied to memory, if you inject glitch over there, you might be able to have one of these pointers actually end up into processor PC, in the register PC. So this would be pretty powerful because depending on the pointer you set here, your PC will jump somewhere else. So you are able to control the program counter just by setting pointer and being able to do something that we are going to explain now. First, does it actually work? Well, we demonstrated this in 2016, and it was quite easy on ARP32. So you see a bunch of instructions here where we load into register R3, R5, and R6 what is pointed by location R1. So this is, you are loading multiple registers from this address. So this is actually, it's a mem copy loop. This is how it works. You copy 4 registers, and you actually store for register a different location. So copy, store, and this is actually it's a memcopy. But one glitch does not only necessarily skip instruction. This is has been one of the biggest assumptions, I think, in our history of fault injection. A glitch can actually do anything. So basically, in this case, you can imagine that the fault that you have injected is doing something differently. It's affecting the opcoded instruction. And if you affect the opcoded instruction in a, let's say, in advantageous way, you might end up with an instruction that actually load what is pointed by your memory into your program counter. This was demonstrated in 2016 already. So this means that what is pointed, so what is in memory, ends up in your program counter. So no, we are not skipping anything here. We are just affecting the program counter by taking data, which is transferred, and moving that to PC with an advantageous fault. This is a fault model we call instruction corruption. Also, we demonstrated that by using instruction corruption, so by assuming that we can have faults that are instruction corruption faults, then we can also demonstrate this for all the other architecture and not only on ARM32, basically. There is one important relevant difference here between ARM32 and the other one. We are going to briefly touch upon in the following. But at this moment, have a look how we actually are doing this attack. Exactly as before, what you are copying now is not the bootloader, it's pointers. But nothing actually changed. We just expect that our fault, our glitch that we inject, sorry, will be able to introduce a fault which is different. So it's not now that we every fault is good. Is we need some specific kind of fault. That's why we say that we are applying that fault model because we expect we would like to have that kind of fault. So we basically start injecting glitch in the small attack window while the bootloader is copied. So we know that this is copied. And this is copied all the same things. So we just focus here, hoping that in that time frame, we are able to generate, to introduce the fault that we need. So basically, what we are seeing here is that we have a glitch, another glitch, another glitch, another glitch, and another glitch. Actually, we tried 1 million of glitch. We were not able to do it. This actually was not successful, and there is nothing to be ashamed of. Actually, this is the way you progress, and for us, it was a reason of progressing. Why? Because exactly as I was explaining, because we are causing faults, but not the type of fault we need. Well, first, we can think that if we are at a different location, we can trigger a different kind of fault. This is something that we already can, we already know. We know that if we just stop where we are, we will fix the probe where we are not producing the faults that we need. So basically, what also we did is that we fixed the probe there in order to minimize the glitch parameter set space. We tried to say, okay, we don't look around in space, so we just need to focus on power of the A. But unfortunately, if you actually minimize too early, so if you don't explore too much, you might take, let's say, a road, an avenue, which might not necessarily be successful. So sometimes you need to minimize in order to be successful, but sometimes you minimize too early, making a few assumptions, and that results into failure. So basically, we went back in our assumptions. So maybe we need to change location because we have a different fault, and maybe the kind of fault we were able to inject is different. So now we changed the way our physical parameters. We changed the glitch that we inject because we moved to another location. So after 300,000 experiments, we actually do see one success story, and this is quite interesting. And you're seeing that we see visible patterns related to copy loop operation. So this means that there is some structure in the way the data is transferred into memory. And this is visible also in the way that our glitch affects the behavior of the device. So for example, you see that this color is a checksum error, which you don't necessarily see around in this area, and this is repeated. So this means that there is a repeated process that if you hit here, you're going to cause a checksum error, but if you hit in a different point in time with a much more precise granularity, you don't get a checksum error. So basically, this is where our successful fault was. So this is also a bit what experience teach you in time, basically. So we would like now to increase the success rate. What we have been able to do now, we have been able to control the program counter. So basically, after fixing the power and the delay to this location, we are able to get a much better yield of our results, because then we are able to control the program counter with 2 successful glitches per minute, and where we load an arbitrary value into PC. So at this point, we have a way of controlling the program counter. So why does this work? Well, this is a very good question, because in a copy loop, in Extensa, we actually have a similar pattern of transferring data by copying into a register and storing into a register. But there is one very big important point here, that in Extensa, like in many other architecture, you don't have an instruction that, if modified, is going to load directly PC. You cannot address PC directly. There is no instruction like that. ARM is quite peculiar in this part, ARM32 actually, where you can use PC as a destination register, like put this value in PC. This is quite an interesting design choice, but this is not available in Extensa. So why this is actually working here? Well, we think that this is because what we are about to explain. So there is this memcopy loop, and the register A0 is used for the return address. So in other words, when you return from a function with the instruction redwn, you actually set PC to A0. So what we think is happening is that our instruction is loading something into A0 rather than into another register. Good. So this means that when you exit this function, you are going to set the PC to the value of A0. Great. Well, this may looks like what you achieve in a very simple buffer overflow, when you actually overwrite the PC on the stack, and the PC is actually restored at the exit of the function. For the restoring part, we are exactly in that situation. The point is that there is no buffer overflow here. We are just loading our data into a register, which is then going to be transferred into PC. So this is a control PC, which is indirect. Well, we think that nothing can stop us now. So let's enable flash encryption. Well, it's used to protect IP implemented in software. And the data is encrypted using a tweaked AES-256 algorithm. What is relevant is when you enable flash encryption, the decryption is done transparently to the processor. There is encrypted data, there is a flash control that is decrypting this, so there is actually no decryption process happening in the processor, and the decrypted data is directly fed to in memory and to the CPU. So basically, we cannot perform the easy exploitation anymore. Why? Because if we put our pointer here, they will become completely garbage here. So we cannot use that technique. And actually, Expressive advises their customer to enable this feature. But there is also something that is going to play quite a role in our presentation. There is a UART bootloader. The UART bootloader mode is implemented in ROM. It's used for recovery for programming the flash. So basically, what you have is a mode that you can enter by setting a strap pin before resetting the chip. So you actually set a pin to a specific value, a specific pin to a specific value, and then you enter into this mode, where you can actually issue commands, where you are able to read and write the flash, to read and write register, and you are able also to load and execute code from SRAM. So it's really nice. You actually push your code into SRAM and say go, and it will just start executing your code into SRAM. And also it cannot be disabled. So this is something that will always be there, and by executing with arbitrary code, we're using your bootloader mode. we actually set the boot chip in your loader mode by setting the external strap pin. And then after pushing our payload, we use the load RAM in order to execute the code. Basically, also the Expressive SDK supports that. So it's really easy to do that, and we don't expect anything to, let's say, to be done other than just using the SDK. No, indeed, this cannot be disabled. As I was saying, Expressive is fully aware of this, meaning that if you actually would leave these enabled, you would just make flash encryption useless, because you load stuff into memory, and we can use the bootloader in order to read out the flash content. So Expressive is actually aware. So there is a fuse that does not disable the USB, the boot ROM mode, but boot ROM, but it prevents the extraction of plain text flash contents, meaning that you can still send commands, but you are not able to read the flash in clear text. So the transparent decryption of flash data is bypassed. So if you are in your bootloader mode, then you will be reading exactly the encrypted data, and it is no decryption performed. So this means that the value of these fuses is preventing, but also we know that it's checked, it's combined with the strap pin, which is resampled after system reset. So you reset, the strap pin is sampled for understanding which mode you are. And if you are in your bootloader mode, then this fuse setting will prevent reading that out. But there is an interesting observation here that we would like to share and apply. Keep in mind that what we are going to share, you're going to see more details in our blog post quite soon. But there is something interesting that the CPU has an internal SRAM. Yes, that's exactly where you load your UART bootloader into RAM, into memory. The data in internal RAM may be persistent across one reset. So what happens if basically you write to something into SRAM and you reset the SOC into some mode or in some way in doing a warm reset, and the SRAM may not be actually affected by this, unless, of course, it's overwritten or specifically erased. So this is something that we always keep in mind, which might be interesting, and we have been using this for this attack. So let's look at this behavior in detail. This is the idea. So if you actually reset the chip with something with your bootloader in SRAM memory, in SRAM, you just put arbitrary data. If you actually do perform a cold reset, what you will end up if you reread the SRAM afterwards is just garbage after a cold reset. But there is another behavior which we're able to research and investigate. We fill the SRAM memory with arbitrary data. We do trigger a warm reset by controlling the SOC watchdog from software, and we issue a warm reset. So basically, we load our payload in SRAM, and then by writing some registers that we've been able to identify, we have been able to trigger a warm reset and not a cold reset. But this leaves our data in memory completely untouched. So how can we abuse this? Well, we can use this for executing persistent code. For example, one way, or the way that we wanted to try, is that you prefill your memory with code, and we are going to use a command handler here that allows us to do the watchdog reset. Then we have a NOP, and then we are printing as a payload, basically as our shell code. Basically, we are printing on the serial interface for saying, hey, you succeeded in this attack. You have been able to execute this guy here. So after we load this payload into memory, we reset the chip by issuing the watchdog reset. So we are doing a warm reset. That payload is still there. But what's happening in the meantime? That the chip is booting, right? And this means that the bootloader is being copied from flash, and it's overriding our payload. So basically, we tried, okay, maybe we are able to stop the loading, and we are able to fall through in and execute from here. You never know with fault injection, so you can test all the crazy ideas. And this was our first attempt. We do just glitch and pray. That's actually, we thought a bit more about it, but we say, okay, let's do this and see what happens. This seems quite a good idea. Then glitch, then glitch, then glitch, then glitch, then glitch, and we reached again the 1 million experiment threshold without any success. Nonetheless, we had unexpected results. That's why failing is can be different. You can totally fail, or you can fail with something interesting, and this was the case. So we failed badly, but we had something really unexpected. So the exception PC, so the PC where the exception was caused, was something completely unexpected. And the reason is that this execution address is not within the SRAM execution. So we wondered, how is this possible that this ended up there? Where does this come from? And then this is the value, 661B, 661B. And let's have a look at what is in memory at that moment. I mean, the ROM, we know, we were able to dump. The SRAM, we just put it. So, I mean, this value needs to come from somewhere. So we had a very big surprise when we look at the handler and we look at our 1000 add instruction, and this is the printing code. So there is really nothing really special. So there is this big payload here, and if you translate that to data and you look at that in the XDump, you see that this is exactly what goes in the PC. So just to make you think about it. So we put this into memory. The bootloader is overriding this. We glitch while the copying is happening, and out of magic, the value which was already there in SRAM, which was being overwritten, ends up in the program counter. If anybody has a good explanation for this, we would like to hear and add to our hypothesis. So basically, to add the instruction of the payload which wasn't there ended up in the PC register. So this is actually allows us to set the PC to an arbitrary value. So without overthinking, we can actually do another kind of attack immediately. We use the bootloader to prefill SRAM. We reset. We do exactly the same attack. And then we have pointers here. We don't have an add instruction anymore. That add instruction that has been replaced with pointers, but this actually now allows us to end up in PC. So we control the program counter with the payload that we still have somewhere. Okay, this is like a very good recipe for success. So when this happens, and our pointers that we set ends up into PC. So basically, this attack in the end was successful, and we are able to jump wherever we want. How do we use it is going to arrive in a few minutes. Why does it work? Well, we exactly don't know, but there are a few scenarios which are imaginable. There is one which is extremely interesting, for example, that, for example, we know that the data being transferred, so that goes from your source to the destination, can be put into your program counter. This is what we already explained during our initial part of the presentation. But what if, for some reason, the source and destination are actually swapped or changed? Then your source becomes the destination. It's a very wild hypothesis, we know. There are scenarios possible. But what if the data where you are transferring to can be loaded into PC? Well, we don't know. This is surely part of something that we would love to continue our research with. But as you can see, as soon as you unlock your thinking from skipping instruction, and this is what we would like to share with the research community, let's stop thinking about skipping instruction, because that's not the only thing that happens. And there are beautiful scenarios here that can be triggered and which are unexplored. So basically, both the data, the source and destination can actually play a role here. We are not there yet because we have control where we cannot access plain text data, but we can jump wherever we want. Beautiful. So we have control of PC, and why not jumping to your bootloader? Because now we are booting in normal mode. So that bootloader which is in there can access the flash encryption, because the boot that has been done here in this mode actually was perfectly fine. So there was no strap pin set. So basically, we can read the plain text data by using this, the function in the your bootloader. So basically, we identify this function by reversing the ROM, and we would like to jump to a place where we know that prints something when we are able to identify our success. So basically, after we are successful with the glitch, we simply have everything in place for dumping the code from the board. But unfortunately, this did not work. This is not exactly what we expected to. So we tried to something else. So instead of jumping to the overall bootloader mode to the start, we just jumped to the command handler itself. So there is no string being printed to check for success. So basically, every time we glitch, we send the command, "Hey, are you alive?" Just with a small your timeout. And if the chip responds, the SOC responds, then basically the chip is working, and we are able to use that command handler to access plain text data. So in summary, we have been able to bypass secure boot plus flash encryption and extract the plain text flash data using a single EM glitch by leveraging and also without knowledge of the decryption key. We don't need the key for doing this attack. So we are able to bypass the encrypt secure boot by applying a different fault model, and basically we don't need the decryption key. We did something similar in 2019, but still on ARM32. So we wanted to really try this on a SOC which allowed us to apply our new techniques. So what is the impact? So we've been assigned to CVs, both for the SRAM persistence, which was not expected, plus the pure bootloader mode. This is the single CV for this attack. And we have also another CV, which is not described in this talk. And the attack only applied to revision 0 and 1 of the SP32 silicon. The new version 3 supports new fault injection checks and disable the your bootloader functionality permanently. So rather than prevent it to read flash, you disable the bootloader in detail. So if you want to find more details, they are in the Express advisory. And we're going to share more of these and the rest at our website. And that's it. I hope you enjoy it.
Thank you, Cristofaro. Friends, if you have any questions, this is the time you send them across via the Zoom chat. Okay, I don't see any questions coming in from anybody. That could be two reasons. Okay. There's one question. There are two questions. Okay, sorry. Let me read them out for you. Can you explain it again? I was late. Oh, sorry. You can watch the webinar, which is uploaded on our YouTube channel later.
Yeah, I think that's the best approach. And if you have questions, just feel free to ping us in online and channel on our email. That's perfectly doable.
All right. There's another question. In the process of injecting, what are the possibilities that the device could get damaged due to injection at wrong place? This might
No, please, is there more?
Yes. I think the second part of the question is this might be common in voltage glitching, but how was your experience with regards to the same with EMFI?
Yeah, no, that is a very good question. And yeah, it can happen that you have casualties in your process, that's for sure. Especially because the power that you are exerting on the chip, first, it's an impression that is focalized in one place. It is not true because the EM field as a usually, at least in our case, as a radial symmetry. So this means that you're not necessarily glitching where the probe is. You may be glitching something which is nearby the probe and you don't know. So also it may happen that the power that you're using may be too strong for, let's say, for what you are trying to affect, but maybe enough for affecting the component nearby. So yes, there is enough possibility to to affect the target. So basically, advice would be start gentle. Even if here starting gentle, maybe it's something that does not necessarily is related to damaging a chip. I think I don't have other advice other than this. Start exploring. Do not assume that the closer you are and the stronger you are, the better it is. Actually, it might be the opposite. So these are two other things. But I think that for now is what I can think of. Maybe Niek.
But I think to maybe say in general, it does not happen too often that the chip breaks due to the glitch. So typically we're not that careful. Of course, situation is a little bit different when you do not have multiple targets, so it becomes a bit crucial to keep them alive. But for example, for this ESP32 platform, we've been injecting as strong as we could at various places on top of the chip, and we had no damaged chip whatsoever. But it may, like Cristofaro said, it's always good to keep it in mind that it can happen. And so if you do not have enough targets or you want to keep the target alive, it's a good advice to to start not by hammering it too hard immediately.
All right, there's another question. Let me read it out. I believe this is also in two parts. About the placement of EM probe, how precise you have to position the probe between attempts. I think the second part is how picky the successful glitch is regarding the placement of the probe and how repeatable it is. Or do you have to scan the whole chip area between individual ESP32?
Niek, you want to take this?
Sure. The ESP chip in specific is quite sensitive, but also is quite small at the same time. So typically what we did, we just scanned the whole chip with quite a, I think we always used a 30 by 30 grid. And then typically we found a location where we had success and then we simply fixed to it. So we did not really explore at a fine granularity for the ESP32 to see what the differences are when you start moving the probe with really small steps. I know from experience on other chips that this can have an impact, and there it really matters if you have it just misplaced a little bit, and then basically the behavior of the chip is completely different. Now, it's important to realize that the location of the probe and the glitch parameters themselves, being the timing and the strength of the field you're injecting in the glitch, they're all related to each other. So typically it's quite hard to figure out if it's really because the location is important or that the location just means that the power that you need also changes. But in typical fashion or in typical attacks, or at least for the characterization, what we do is that we take quite large grids and then we are able to find vulnerable locations. So that already means that the location is important, but it's not super crucial at the very fine granularity of the position.
One note here, of course, the experience may significantly vary depending on, let's say, on the setup that you're using. And so these are all physics variables which can be affected by temperature, maybe. Yeah, we also experienced that. So we have seen glitches disappearing, meaning that not being able to glitch the target anymore because the temperature in our office actually changed. So we have seen this, and so comparing different setups can be really challenging from a results point of view. If you compare them from other, let's say, in other dimension, that makes sense. But from a result point of view of that specific result, that might not even be reproducible exactly that with exactly another equipment. Usually you can. But once you've found your parameters with your setup, then with the glitch becomes pretty reproducible. And we were able to get easily like 2 glitch per minute. which is quite interesting in general for, let's say, for an attack that needs only to be successful once.
All right. Anybody else has any questions to ask? Well, I think that's it. Nick and Cristofaro, thank you so much. For the audience, if you would like some more information, please contact them.
Andrik,
yeah.
Before going, we will have final thoughts, because
Yes,
I think it's important to share. Actually, most standard embedded technology are vulnerable to FI attacks. So basically, what we shared here is not surprising and should not be surprising for anybody in the field. So this is not our intention. Our intention was mostly to share some research, but also showing that how fault injection alone, I mean, it's really in its early stage, and you can combine these with other techniques, and you make your fault injection exploits much more effective. For example, the fact that here the your bootloader could not be disabled, or even leveraging the persistent code in SRAM across resets was another very important point. So this is something that is not usually done so much. I mean, most of the experiments that we actually see and read about is I bypassed this, and this is my setup and it worked. Bye. We think that the full potential of fault injection attacks are still unexplored. So we think that if you start using creative use, having a creative use of fault models, and also with the applied to specific targets, we think that this could be give rise to unforeseen attacks. So basically our thoughts here are there is much more to explore, and this is what we wanted to communicate with our research. And we already took the questions, but now I think we are perfectly done.
That's nice. Anybody has questions now to ask? All right. If you have, you can please send Nick and Cristofaro an email, and they've also mentioned their Twitter account. So please give them a thank you shout out on social media. Highly appreciated. And please also send us feedback if you like this webinar. If you would like to give a webinar, we would like to hear from you as well. So yeah, thank you so much, everybody. And do join us for the upcoming training and conference scheduled from the 27th of September to the 2nd of October. Thank you, everybody.
Thank you very much. Thank you.
Thank you.
Bye.
Bye.